Okay, what about now? Can you hear me now? Is this working? Let me try. I think this is working. Is it working now? Wait, you got, oh yes, I've made everything work. Oh my goodness. Oh my God. Well, that is good. Thank you for sticking with me and helping. Okay. Oh my goodness, it was all supposed to be simple. Right, here's my plan. Okay, I'm gonna come on each night. I'll try to do every night. I'll try to do more if I can. I'll try to give notice if I can. I'm going to do a combination of using the Anki cards to just do a random things you need to know for the A-level maths, and then you can jump in, and if it throws up something that we need to talk about, then we can hop on and talk about that. If you have specific questions or specific topics that you already know are a major problem, then just tell me and I will do that instead. Okay, so this will give us an opportunity to pick up something that's a problem, or you can say I already know that this is the problem, and then we'll do that. Okay, so area of a trapezium, where does this come up? Trapezium rule. Oh, n in n. Okay, so n in n, this means natural numbers, 1, 2, 3, 4, that kind of thing. You'll see this notation in proofs. You have to know what these are. N and Z and Q and R. All of those you should be able to recognize. This is all numbers, basically. All, because you don't know about complex numbers, so this is all the numbers. This is rational numbers, which is fractions. This is integers, which is the same as natural numbers, but integers you can include plus or minus, and you can also include 0. So you'll see this in proofs, not really anywhere else, and those are the ones that you have to know. Yeah, proof. Now, by the way, proof you can more or less skip, okay? I'll go through, I can just quickly, let's do a summary of what's in the A-level and which bits are important and which bits are not important. So you've got in the A-level, I think of it like this, one like this, okay? So these are the things that are worth about 20-25 marks, lots of marks, very important, very big. This is lots of marks. This is differentiation and integration and trig. Those are huge. Each of those is worth about 20-25 marks. Very, very big, lots of marks. Then we've got things that are worth about 12 marks every year and things that are worth about 8 marks every year. The 8 markers, these are the things, I'm just going to turn my brightness down a bit so I don't feel quite so much like it's going to give me a migraine. Okay, so the 8 markers, you've got functions and modulus and parametrics. So these are, yes, they're important, but they're not things that you should spend ages and ages on. You're only talking about 8 marks in the whole of the 3 papers. Of these, the easiest to get the marks on and sort out is modulus. We can sort out modulus super duper quickly. Then the next easiest one is just being able to basically differentiate and integrate parametrics, because that's not difficult to put together the way that you differentiate and the way that you integrate parametrics. So even if you don't fully understand them, you can at least get to the point where you can pick up half the marks. And then functions, you've got composite functions and inverse functions. Don't worry about domain and range. Domain and range is 1 mark. 1 mark. Domain and range is really not, domain and range is not stopping anyone from getting the grade that they want. It is 1 mark. It is just using up your revision time if you worry about it. To find the range of a function, you sketch the graph. So already that's got rid of loads of students who don't like graph sketching. So to find the range of a function, you sketch the graph and you literally look at your sketch and you see how high does it go and how low does it go. That's it. So it's 1 mark, it's not a biggie, it's almost not worth worrying about. which I would also say is true about proof. Like proof, I'm going to just put, it's not even, the thing about proof is you can spend forever, you could spend the whole year working on proof and still not be able to get the marks for proof. There might be ones you've seen before and then great, you can get the marks, but what proof is doing is it's sapping loads of your revision time and not really giving you much reward in the exam. Whereas differentiation, integration, trig, if you put your revision time in there, you will get massively rewarded in the exam. Domain and range is like the extreme. You could spend ages and ages and ages on domain and range and still not get the 1 mark. So you need to be strategic with the time you've got left. We've got 4 weeks. So the strategy needs to be there in terms of your revision. Be aware of what's worth the marks and what isn't. Be aware of what you can improve on quickly and what will take a long time to improve on. So proof will take a long time to improve on. Modulus won't take very long to improve on. So those are the 8 markers. Everything comes up every year in maths. So it's not like any other subjects where it's like, oh, I wonder if it will come up. There will be a question on composite functions. There will be a question on inverse functions. It's just a case of which one. There will be a modulus question. There will be a parametrics question. There will be a few differentiation, a few integration, and a few trig. The 12 markers, this is sequences and series. That will be 2 questions. One of them is going to be on things like sigma notation and recurrence relations questions. UN plus 1 is blah, blah, blah. And then you've also got arithmetic and geometric. Now, the arithmetic and the geometric, you can do the same technique for every single question, and it will always work. The sigma notation and the recurrence relations, they are absolutely fine if you don't panic. They look scary, but they're not scary. They're easier than, it's kind of like you've taken the easiness of it and hidden it in notation, and then students just think they can't do it because it looks so scary. Yeah, exactly. It's really, really easy so long as you don't panic. Arithmetic and geometric series is all about simultaneous equations. They're going to give you some information. You translate that information into equations, and then you do simultaneous equations. Same every time. So if you don't draw a little picture, then you're unlikely to be able to see what to do. So this is lines and circles and sectors, and lines, circles, sectors, vectors, triangles. A lot of these essentially rely on the picture that you've drawn. Once you've drawn a picture, it's kind of obvious what to do. Well, no, not always, that's a lie. Once you've drawn the picture, it's possible to see what to do. Whereas without the picture, it's really hard to know what to do, almost impossible to know what to do. Those ones are hard. Yeah, I can do whatever you like. Basically, I'm just going to hop on each evening and do what you like. But I think it's good to use the Anki cards as a basis to see what comes up. So maybe if we do 15 minutes of that. Approximations is Newton-Raphson, trapezium rule, iteration, trap rule, and small angle approximations. Functions, modulus, parametrics. Then on the right hand side, we've got things that come up throughout the paper. So these are like everywhere. So it's hard to calculate how many marks these are actually worth, because it's 2 marks there, 3 marks there, 1 mark there, 4 marks there, all that sort of thing. So these are worth a lot, but they're spread around. So you've got exponentials and logs, often tested in integration. Exponentials and logs, you've got algebra and graphs. So in the algebra, I'm talking about things like quadratics and cubics, factor theorem, algebraic division, partial fractions, binomial expansion, that kind of thing. In exponentials and logs, you do get exponential equations and log equations, where you're using rules of logs, or maybe it's a hidden quadratic. But the big ones that are worth a decent amount of marks, also your log rules come in a lot in integration. The big stuff in the exponentials and logs that second years often forget about, one of them is the log-log graphs. and the other one is exponential growth, so like context questions, populations growing, that sort of thing. So context, modelling, exponential growth, that kind of stuff. Partial fractions is, when you unadd the fractions, so you find the a and the b that go on the top of the two linear or for repeated roots of quadratic bit. Finding the a and the b. Again, you would use that a lot in integration, so that's when you would be using the partial fractions. Okay, I'm going to go back to the Anki cards, but if you think of things, so proof, basically, don't worry about proof. Proof is not going to stop you getting an A star, or whatever grade it is you're going for. Proof is a time sucker. Do past papers. Yes, have a look at the mark scheme, work through the proof, see if you can understand how to do it, but don't get stressed about proof. Don't spend ages and ages on proof. That's not going to be making all the difference. Okay. Easy. Right, area of a trapezium. This is mostly in the mechanics where you're doing trapezia that look like this. So you've got A and B, and then the distance between them is h, and the area is half h, A plus B. Let's put all of these easy so they don't bring it back. Yeah, but if the thing that is costing you marks, if you imagine going forward in time, you're going to have to do a paper in 2 hours. If you run out of time, then you're missing the opportunity to show what you can actually do, and then you're going to go down 2 grades. So all the revision in the world is great, but if you can't go at the pace that you need to go at, and if you can't work under pressure, you're not going to be able to show what you can do. It is the absolute biggest mistake that students make when revising, is they work topic by topic, and they go through each topic and they learn as much as they can and practice each topic, and then they walk into the exam and they're like, I have done all the topics, but they haven't done lots of papers in time conditions, and then they go down by 2 grades of what they should deserve relative to what they actually get. Topic by topic revision is the biggest mistake that students make. Okay, this is a classic. You are expected to know exactly what to do when you see this. Sine squared is not something that we can integrate. We have to change it, and we have to change it using the half angle formulae. Sine squared x is a half minus a half cos, and then whatever that angle there is, make it twice as big. So that's a trig identity. Hardly ever use it in trig questions. We mostly just use it in integration questions. You're right, it does come from the same group of trig identities, the double angle formula. So sine 2x is 2 sine x cos x. But what we're using here is the cos 2x one, and specifically we're using cos 2x is 1 minus 2 sine squared x, and then we're rearranging this. So if you rearrange that to make it say sine squared x equals, it says a half minus a half cos 2x. You differentiated it, in which case you're right. The derivative of sine x all squared, hang on, let me get rid of this. So make a bit of space. So if you wanted to differentiate sine x squared, you'd need the chain rule. You pull the 2 down, change it to a 1, multiply by the derivative of sine x. So the derivative of sine squared x is 2 sine x cos x, but the integral of sine squared x can't be done until you use that trig identity, and then you can integrate. So you get a half x, and then this one is going to be sine 2x, and I left a little gap there in case I need to include a number. So I know that sine differentiated is cos. So sine 2x differentiated is cos 2x times 2. A 2 pops out when you differentiate. So because a 2 pops out when you differentiate, I need to put the reciprocal of 2, the thing that kills off the 2. So this, which half? So this equation rearranged, no, not that. Sorry, get rid of this. there's no rubber with this. So cos 2x is 1 minus 2 sine squared x. If you rearrange that, you get sine squared x equals a half minus a half cos 2x. That is what you have to use to integrate sine squared. So this half is this half, and this half here I put there because otherwise it would be wrong. So let's say I didn't put that there, that half with the star on. Then I would be saying that if you differentiate sine 2x, you get cos 2x. Differentiation is the opposite of integration. So if I'm integrating down, that's the same as me differentiating up. So whatever cos 2x integrates to is the thing that when you differentiate it, you get cos 2x. So if I don't put that half there, then the 2 that comes out from the chain rule, when you differentiate sine 2x, you get 2 cos 2x. So that 2 that comes out, I need to put it upside down in the integral. I know it's difficult. Integration is the hardest thing. It's just difficult. It's a really difficult thing, integration. So the first half with the arrow, that's just the half from that was just sitting there. And then the other one, the one with the star, that comes out to kind of undo the chain rule, to kill off the thing that comes out of the chain rule. Okay, this one is hard. Describe this transformation. First word, I'll try to give you like a few seconds just to jot something down. The first word that we're looking for is translate. No, it's not. First word that we're looking for is stretch. Usually get a mark just for stretch. Now the scale factor of this transformation, because the a is outside of the brackets, yeah, with the previous one I was using my method of integration, which is that you know what was differentiated, so you write that down, then you differentiate it to see if any numbers come out, and if so, then you compensate for those numbers by putting a fraction in. So if a 2 pops out from the chain rule, you would put a half, and if a 5 pops out, you'd put a fifth. We could do a whole session on integration easily. We could do months on integration. It is really difficult, but they'll crop up in here, so we'll do them every time they crop up. But if you have a specific one that you'd like me to do, then just let me know. So this is a stretch. It's scale factor A. Everything outside the brackets is doing this to the graph somehow. So the stretch is the first bit. The scale factor A is the next bit. And then we need to say parallel to the y-axis. To get all the marks, those are the 3 things that you'd have to put to describe that transformation. Okay, sketch y equals e to the x, including the equations. So e to the x looks like that. So does 2 to the x and 3 to the x and 4 to the x and 10 to the x and everything to the x. The asymptote runs along the x-axis. Most people think you'd drop a mark if you don't label axes. That's not true. That's very GCSE. Looks like this. This is fine. What's important here? Yeah, maybe the y-intercept. That's always a really easy thing to put on. Yep, perfect, goes through 1. And the important thing is that this asymptote that runs along the x-axis is labelled as an equation. So you can't just put the number at the side. Yeah, exactly. Asymptote is y equals 0, but you have to put y equals 0. You can't just put 0. So it's the equation of the asymptote. Y equals, and all the equations you use in the A level are either y equals or x equals. So the equation is y equals or x equals. This one is y equals 0. And obviously if that gets translated, then it moves with the graph. Hello, I'll tell you what, we'll do 5 more minutes of these, and then I will show you the revision plan that I've put together with a student that I'm working with. to go up 2 grades. Okay, so let's just do a few more minutes of these. Stationary point. Okay, I'm going to actually talk about stationary and inflection because these get muddled up like nothing in the exam. The first derivative and the second derivative do completely different things, and the issue, as is the issue in many things in the second year, is that the first year is taught as if there wasn't a second year coming. Yeah, so in the first year you learn that a stationary point is where dy by dx equals 0, and that is completely true. Okay? They come from my brain, Blue. It's all of everything that you need to know for the A-level maths, everything you need to know. They're Anki cards. I don't know how you share Anki cards other than to literally send someone a link, like on an email, a file that they download, and then they can upload it into their own Anki. So if you've got my email, email me and I will send you the link to the Anki. But I'm going to try and do these every night, so I can do them with you. So yes, stationary point is the same as turning point. Okay? First derivative. Now the first derivative tells you the gradient of the curve. So a turning point is where the gradient of the curve, or the gradient of the tangent to the curve, is 0. The second derivative tells you the shape of the curve, not the gradient of the curve, the shape of the curve, in this sense, in the sense that it's either concave or convex. Concave, convex. This is what the second derivative tells you. The minimum maximum thing, the fact that in the first year they say, oh, you need the second derivative to see if it's a maximum or minimum. Yeah, but no, not that way. So concave bits of graph are bits of graph where if you draw a line joining 2 points on that curve, then that line is under the curve. I remember it cave under. Caves are under the ground. Whereas with convex, if you have 2 points and you join up a line, that line will be above the graph. Increasing and decreasing is first derivative because bits that are going up have a positive gradient and bits that are going down have a negative gradient. dy by dx positive, and here dy by dx negative. So that's first derivative. Stationary point, turning point, first derivative, the gradient is 0 at those points. Second derivative, convex, concave. Concave, where it's underneath like a cave, the second derivative is negative. And convex, the second derivative is positive. So see, they do totally different things, first and second derivative. So why in the first year, when you find the coordinates of a maximum or the coordinates of a minimum, why do they go on about the second derivative? Because the way that we can tell whether or not what we found is a maximum or a minimum is we can find out whether or not the graph is convex or concave at that point, and that will tell us whether or not we found a maximum or a minimum. So look at the maximum point. At the maximum point, any line is under the graph. At a maximum point, the graph is concave. At a minimum point, if I join up 2 points with a line, that line is above the curve. So at a minimum point, the graph is convex. Concave bit of graph, convex bit of graph. This is about the second derivative. So in the first year, when you do the second derivative, and then you shove the point in, and then you go, oh, it's negative. Therefore, it's a maximum. That is true. That wasn't a lie. But what you're actually doing when you find that second derivative and put the point in is you're finding out that the graph is concave. And if the graph is concave and you have a stationary point, then what you have is a maximum. If the graph is convex and you have a stationary point, then what you have is a minimum. Now, what's an inflection point? An inflection point is where the graph changes from concave to convex or vice versa. An inflection point is totally to do with the second derivative, but the inflection point is not second derivative equals 0. Okay? An inflection point is not second derivative equals 0. An inflection point is where the graph changes from convex to concave. Now, at that point, the second derivative is 0. So the graph is going to go concave, 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 inflection, convex, convex, convex. Specifically, the second derivative is 0 because the graph is changing from convex to concave or concave to convex. So you can't just do second derivative is 0, boom, finished, like you can with a stationary point. With an inflection point, you have to do second derivative is 0, and then you have to look a little tiny bit to the left and a little tiny bit to the right of your potential inflection point. And then you have to see, is the graph convex or concave that side? Is the graph convex or concave this side? If it's changing, then you have indeed found an inflection point. Some inflection points happen to be stationary points. Some inflection points are not stationary points. They're very, very different. That first derivative, stationary points, turning points. Second derivative, shape of graph. Convex, concave, shifting from convex to concave. That's an inflection point. That's something that comes up a lot as a misunderstanding with students. Okay, this one's come back because I asked it to. So I'll give you an example. Sine squared 4x. I'll just give you 10-15 seconds. Yeah, I'll give you a sec to do this, and then I'll do the inflection again. Doesn't matter, Blue, how much you look. 0.1, 0.5, a bit. It's a good question, just a bit. So what is the integral of sine squared 4x? We change it. We double the angle. The angle gets twice as big. Okay, now the harder bit. Now that half is that half. Now I'm going to do the integration. What function that I know when I differentiate it would give cos? The answer is sine. So I know that this is the answer because sine differentiated is cos. Now I have to think, if I differentiate sine ax, do any numbers appear? Because if so, I'm going to have to kill them. So sine ax differentiated, I get cos 8x times 8 because of the chain rule. So this side of the board I am differentiating. That's the chain rule. And this process that I'm doing is differentiating. And I'm doing that to see if any numbers come out. There's an 8. Exactly, you multiply by 8 because of the chain rule. There's an 8. Therefore, I need to go back and I need to put in something that will kill off that 8. That's the integral. That's how you do it, that integration. Okay, I'll just go back. I'll just create a new board so that I can talk about the inflection again. So, for example, say we wanted to find an inflection point. Here's our equation, y equals blah, 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 blah. You differentiate it and differentiate it again. D squared y by dx squared equals blah, 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 blah. This function tells you the shape of the graph. Is it convex or concave? We want to find a point where the graph changes from convex to concave. This is inflection. We want to find a point where the graph changes from convex, which is positive second derivative, to concave, which is negative second derivative, or vice versa. So what you do is you put your second derivative equal to 0 and you solve and you get x. Now that may or may not be an inflection point. What you do then is you go left a little bit, like take off 0.1 and get that number and feed that number into the second derivative to find the shape. And then go right a little bit. Add on 0.1. Take that number and sub that into the second derivative to find the shape. What you're hoping for is that the second derivative one side is positive or negative, and the second derivative the other side is the opposite, because that shows you that the graph at that point that you found, one side is convex, the other side is concave, or the other way around, one side is concave, the other side is convex. That's the definition of an inflection point. It's a point where the graph changes from convex to concave or concave to convex, i.e. it's a point where the second derivative goes from positive to negative or negative to positive. So that's the definition of an inflection point, and notice that the first derivative is irrelevant. The only reason we need the first derivative is to get the second derivative. Inflection points are nothing to do with the first derivative, and stationary points are nothing to do with the second derivative. Stationary points are where the first derivative is naught. If we then want to say, I wonder whether I found a maximum or a minimum, then we use that second derivative to find out the shape of the graph at our stationary point. Is it convex? If so, we're looking at a minimum point. Is it concave? If it's concave, then the graph looks like that. So we must have found a maximum point. Okay, how do you find the gradient of a line? You rearrange it to make it say y equals mx plus c. It's the only time we actually like y equals mx plus c in A level, is you rearrange it to make y equals mx plus c, and then the m, that's the gradient of the line. It's not really like upper lower bounds, it's more what's the shape of the graph a bit to the right, what's the shape of the graph a bit to the left for the inflection point. Right, what's the derivative of sec y with respect to x? So we are differentiating sec. Derivative of sec x is sec x tan x if we're differentiating with respect to x. This is what you do when you do implicit differentiation. It's the chain rule. The chain rule says, say I want to differentiate with respect to x, that, with respect to x. Now 4x minus 1 is not x. If I had x to the 10, that would be easy. It would be 10x to the 9. But 4x minus 1 is not just x. It's 4x minus 1. The chain rule says that's okay, we can still do it. It doesn't matter what's in the brackets. It doesn't matter what's to the 10. We can still do it. Pull down the 10, change it to a 9. Just do it as you normally would, but then multiply by the derivative of the thing that wasn't an x. You don't need u equals. Exactly. You can just multiply by the derivative of the thing that wasn't an x. Same thing here. I'm differentiating sec y. What's the derivative? It's sec y tan y. Oops, that's not a word. Sec y tan y. But I've differentiated with respect to y. I've done d by dy sec y. To do d by dx sec y, I need to use the chain rule because it's not an x. So I multiply by the derivative of the thing that is not an x. I multiply by the derivative of y. Chain rule. Implicit differentiation is just the chain rule. It's not even a topic. It's just the chain rule. Geometric series. Okay, we were talking about this at the beginning, geometric series. Geometric and arithmetic series, the way they're going to do the question is they're going to give you some information. So for example, they might say the fourth term is 18. Now what you do not want to write is this. This is not helpful at all. Not for geometric and arithmetic series. So try to remove that notation from geometric and arithmetic series. The fourth term for geometric series, the fourth term is written like this. Is written like that. So this is what they'll put in the question, and this is what you write down on your piece of paper. And then they'll give you another piece of information, and then you do simultaneous equations. It's the same with arithmetic and geometric. Take the piece of information, turn the piece of information into a math sentence, and then you will get a couple of those, and then you do simultaneous equations, and then you will have done whatever the problem is. Same every time. So if it says the nth term is x, what you're going to write is that the nth term of a geometric series is x. If it's an arithmetic series and it says the nth term is x, then you would write the nth term is x. So the sum to infinity of a geometric series is that. So for example, say I had a geometric series and it said the sum to infinity is 112. I would write down a over 1 minus r is 112. The sum to infinity, translated, is a over 1 minus r. Now that sum to infinity, that comes when you do first term, add the second term, add the third term, add the fourth term, add the fifth term, add the sixth term, add la 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 la, and you just keep adding them up forever. So why doesn't that just equal infinity? Well, it does, unless the r is really small. And really small means between 1 and minus 1. So the r is the thing that you're timesing by to get from one term to the next. If that's really small, then what it's doing is it's making the term smaller and smaller and smaller and smaller and smaller and smaller. And then that means that we can add them all up forever, because after a while they're just getting so tiny that even though they are adding on, they're not adding enough to take us past 112 or whatever the sum to infinity is. So you just have to know the formula for the sum to infinity. You have to translate whatever information they give you into an equation, and then do simultaneous equations. That will work for all geometric and all arithmetic series questions. Okay, stationary point. Stationary. This guy tells you gradient. Inflection, second derivative is naught, and as well, the second derivative is positive a bit to the left and negative a bit to the right, or vice versa. It could be negative here and positive here. That's the definition of an inflection point. It's a point where the graph changes from convex to concave, or concave to convex, whereas a stationary point is a point where the gradient is naught. Derivative with respect to x of cot x. All of the ones beginning with c have a negative derivative. Cot has a negative derivative, cos has a negative derivative, and cosec has a negative derivative. All the rest are positive. So this is a negative derivative. Derivative of cot is minus cosec squared. Yes, concave. So a concave bit of graph is where the line is underneath the graph. And therefore, if you found a stationary point and the graph at that point is concave, meaning second derivative negative, and you've got a stationary point where the gradient's naught, then you must have a maximum. That's why that thing from the first year, I don't know why in the first year we don't just use the word convex and concave. It would be so much easier to explain why we're using that second derivative at all. It's because it tells us the shape of the graph at that point. Okay, it's bringing this one back until I say it was easy. So this one I will say is easy. What is the integral of sine squared a half theta? Give you a sec to write it down. we have to change it. We change it to this, and we double the angle. So I made it an easy one. Oh, I nearly wrote half x. It's not half x. We're not integrating with respect to x, we're integrating with respect to theta. Half theta minus. Now this half is that half. Then I look at the function and I go, which of the functions I know, which is only 10, you only know 10 functions. Sine, cos, tan, sec, cosec, cot, e, learn, powers, and other exponentials. Which of those, when I differentiate it, gives me cos? Sine. Okay. What happens when I differentiate sine? Do any numbers appear? No. Okay, done. If any numbers appeared, I would have had to kill them off. But no numbers appear, so it's all right. I don't need to kill anything. Yes, we do not need that second half, though. You don't need that second half. So this half here is like just watching. It's just at the front doing nothing in particular. And the reason that I don't need anything in there is because no numbers appear when I differentiate sine. No numbers appear. Let me think of another example to show you. So, okay, what about, I'll just create a new question just to, so I've got a board. What about something like that? Now, you know what 80% of the students in the country are going to do? They're going to do integration by parts, because there's two things times together. And what they've learned is that if there's two things times together, you use integration by parts. That is so not true. Exactly, not true. Integration by parts is not for when you've got two things times together. Integration by parts is for pretty much only 1, 2, 3 things. There's another couple, so I'll call it 5, but it's mainly 3. Integration by parts is for anything to do with learn at all. Anything at all to do with learn. It's for this, sine, and, okay, I'm not going to write it like that. Basically, it's x sine x, x cos x, x e to the x. Those, anything to do with learn, and those 3. I have also seen x sec squared x, which means that there could also be x cosec squared x. That's it. 1, 2, 3, 4, 5, 6 things. Anything to do with learn, and then those things. The x that I've written, it could be 2x. Could be 3x, could be 4x, it could be x add 1, but no squareds, no cubes, no nothing else, no e to the. So something like 2x sine x minus 1, or 3x add 1 cos 4x, something like that. X minus 1 e to the 2x. All of those are parts, and anything to do with learn. Those are parts. Not this. This, what function out of the 10 that I know, which one, if I differentiate it, would give me that? Which one, if I differentiate it, would give me that? Now, here's the really important thing. If you differentiate 3x squared minus 1, you get just some x's. I'm thinking differentiation here, okay? I'm not thinking integration, I'm thinking differentiation. If I differentiate e to the 3x squared minus 1, I would get e to the 3x squared minus 1 multiplied by, because of the chain rule, multiplied by the derivative of 3x squared minus 1, which is 6x. So, let me see if I can squish this on. If I differentiate e to the 3x squared minus 1, I get e to the 3x squared minus 1 multiplied by, because of the chain rule, multiplied by the derivative of 3x squared minus 1. Did any numbers appear? Yes, a 6. A 6 appeared. I know an x appeared as well. That was part of the chain rule, but that's fine. Look, I've got that there. X e to the 3x minus 1. If you differentiate this 4 is like the halves from before. The 4 is just sitting there watching. Don't worry about the 4. If I differentiate e to the 3x squared minus 1, does a number appear? Yes, it does. A 6 appears. Therefore, I put a 6 here. That is the answer. No need for integration by parts. You can just write down the answer. M1A1. Yeah, exactly. 4 over 6. Yeah. The 4 is the 4. The 6th is because if you differentiate e to the 3x squared minus 1, a 6 appears. So it's to get rid of that 6. So the way that you have to do integration is you have to see that something was differentiated. It's like reverse chain rule, yeah, but notice that I basically did nothing with this guy. Other than to go, oh, you're just there because of the chain rule. Look, here he is. That's how he pops out, because of the chain rule. When you differentiate 3x squared minus 1, that's why he's there. So my answer has nothing to do with x. Now, if I took that x away, if I gave you this question, 4e to the 3x squared minus 1, that's now impossible. Impossible. There's nothing that if you differentiate it gives you that. Nothing. Because the only thing that if you differentiate it gives you e is e. So the only possible answer was e to the 3x squared minus 1. But if you differentiate e to the 3x squared minus 1, you get a 6x. The 6 is no problem. We can kill numbers. But the x is a problem. There's no x there. That was the issue with that one. Yeah, you have to have the x there. Yeah. Otherwise, this differentiated is not that. And that's the integration. Okay, this question was, how do you show that something has a root? A root is just another way of saying that the graph crosses the x-axis, and x-intercepts are where y is 0. So you would take, oh, I've just read the question wrong. I thought it said, how do you show that it has a root at a point, not on an interval? Okay, this is a good point. This notation, I'm just going to create a bit of room somewhere. And I shouldn't have put little dots because now I'm having to do backwards a million times. Okay, so this notation A comma B in brackets, it means two things. It can mean a coordinate, and the exact same notation can mean an interval. So a section of the x-axis, all of the x's that go from A to B is written like that with brackets. So it's annoying. It's the same notation. It means two completely different things. One of them is a coordinate, one of them is an interval. If I want to show that a function equals 0 somewhere between A and B, then I use the change of sign argument. Yeah. So I do f of A, and that comes out positive or negative, and I do f of b, and that comes out positive or negative, and then I write the sentence, and the sentence has to say there is a change of sign, and the function is, there is a change of sign, and the function is continuous. Therefore, there's a root between A and B. You can't just say change of sign. There are lots of graphs that change sign, but there's no root. There's an asymptote. It jumps over the asymptote. Yeah, has to be change of sign and continuous, therefore root. Okay, we've got 3 more minutes. What was this one? It's the derivative of sec, but it's sec y, and I'm differentiating with respect to x. Chain rule. go ahead and differentiate and then multiply by the derivative of the thing that wasn't an x. Oh, I don't know why I put hard. Okay, geometric series. Let's say I gave you a geometric series and I gave you the following information. The fourth term is 9. The sum of the first 8 terms is 50. So this is a geometric series. So you translate the fourth term is 9. The sum of the first 8 terms is 50. The fourth term is 9. The sum of the first 8 terms is 50. Then, simultaneous equations. Same thing every time. Make the first one say A equals, sub it in the second one, fiddle, 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 rearrange, rearrange, solve, 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 done. Same every time. Okay, I am going to stop now, but I'll try to do this each evening in May for you, and I'll try and set it up so that you get a notification. And anything in particular that you want me to do, you can always just give me a shout, because I can switch to this and do questions. So if you've got questions you want to save up for me and bring to this hour, then you can. Okay, see you soon. Oh, I'll tell you what I didn't do was answer your question about going up 2 grades. So we'll do that tomorrow, okay? Tomorrow I'll talk about what is the best use of your time in the next 4 weeks to make you go up 2 grades. Okay, see you.